Hello everybody, welcome back to another geometry lesson. Today we're talking about section 5.3. Now, last class we discussed how in order to prove two triangles to be congruent, you need to show that all the sides and all the angles are congruent. That's quite a bit of work. So today I'm going to try and show you ways of proving two triangles are congruent without as much effort. That's going to start here with our first theorem, the side-angle-side congruence theorem. Let's say for a moment that I have two triangles. Let's say that one of these triangles looks like this, and the other one looks like this. They look like they could be congruent, but in the past, in order to prove they're congruent, we would need to show that all the sides and all the angles are the same. What we're going to be learning today is that we don't actually need all that information. We can shrink down our checklist. The side-angle-side congruence theorem says this. If you can figure out that a side on both the triangles, the angle next to the side on both of those triangles, and the side next to that, all in a row, are the same, the triangles are the same. It requires them all to be in a row and directly next to each other like this. I didn't skip any sides or angles. But if you can get that happening, you can prove the two triangles are the same. So let's look at the actual theorem. The theorem states that if two sides and the included angle of one triangle are the same as another, in other words, if they're congruent to each other, then the two triangles are congruent. And the triangles are congruent. I took note of something very important here. Of course, we need these three pieces of information to be the same across both of them, but I also mentioned an included angle. The included angle, so the included angle refers to the angle caught between the two sides of both triangles. You see, the reason why we're calling it side angle side is because the side, the angle, and the side all in a row have to be congruent. It doesn't work if it's just any random sides and angles. It has to be the angle caught between the two sides. So our whole purpose for doing this is to see if we can prove things a bit quicker. It would make sense for us then to take a look at a proof. So, for this proof, we are given that BC is congruent to DA. That's why we have these congruency tick marks. And we're also told that BC is parallel to DA. Anytime you see parallel lines in one of our proofs, we should think about what we learned in Unit 3. Things like alternate exterior, alternate interior, corresponding angles. That should come to mind. Let's start by writing down our given. BC is congruent to DA, and BC is parallel to DA. Those are our givens. So we're trying to show that these two triangles are congruent. The first triangle is the one up top here, on the top left. The second one is on the bottom right, here. If we really want to show that these two triangles are the same, we need to show either that all 6 sides and angles are the same, which is a lot of work, or we could use side, angle, side. We just need to find a side, angle, and another side all in a row that are the same. Well, looking at this, we see that we have two parallel lines. And we know something about parallel lines. When you have two parallel lines cut by a transversal, it forms a whole bunch of different fun and congruent angles. Two angles that form in particular are the alternate interior angles, and we know that those are congruent. So let's start off by writing that down. We can't just call this angle C because there are two angles here. I'm going to call it angle BCA because it goes from B to C to A. And I'm going to say that's congruent to angle DAC. So, how do we figure this out? Well, that's because they are alternate interior angles. It's the alternate interior angles theorem. Okay, we're getting there. The only thing we need to show now to show that these two triangles are congruent is to figure out what that third side is. And this one's a bit hard to see. Again, on this triangle here, we have the side and the angle. It seems like the side that we're trying to find is this one, from C to A. But on this triangle, isn't it also sort of A to C? Isn't it that same line that we're trying to find is congruent? Recall that something can be congruent to itself. CA and AC are the same line. So we could say that CA is congruent to AC because of the reflexive property of congruence. Now this diagram looks like a lot, but let's analyze it. On this top triangle, we have a side, an angle, and a side, and that angle is included between the two. On the bottom triangle, we have a side, an angle, and a side, and again we have it as an included angle, and we know that all of those are congruent to each other. Because of this, we can say that by side, angle, side congruence, the two triangles are the same. We can say that triangle ABC is congruent to triangle CDA because a side, angle, and another side are congruent on both of them. SAS congruence theorem. Very nice. This is just one way that we can show that two things are congruent, and it's a pretty quick way of showing it too. Let's flip to the back page and see how we can use this in addition. So, in the diagram, M is perfectly in the center of the circle. And we're trying to see if we can conclude anything about the two triangles in the diagram. Pause the video here and see if you can figure out anything about these two triangles. I'll give you a hint. There's actually quite a lot we can figure out about them. Pause the video and try this one out. Hopefully you had a chance to try this problem out and I wasn't just sitting in silence for 5 seconds. So let's take a look at it. In this diagram, if M is perfectly in the middle, let's look at how this interacts with some of the other information we know. If M is perfectly in the middle, that means it's also in the middle of this line segment RP, right? Well, that means that it bisects RP. We know that since M is in the middle, RM is congruent to PM. And the same could be said with S and Q. M is directly in the middle, so SM and QM are congruent. For those who are observant, you might recognize that these are actually the radii of the circle, so they're actually going to be the same to each other as well. But we're not too worried about that. The important thing is that we have found two sides that are congruent to each other, two pairs of sides. If you wanted these triangles to be congruent, what angle we need to show is congruent? Well, we need to show that this included angle is congruent to this included angle, the ones that are between the red and blue sides. But we do know that those are congruent because of vertical angles. Angle SMR is congruent to angle QMP because of vertical angles. So we can actually say something really big about these two triangles. Since we have a side, an angle, and a side on each of them that are congruent, and the angle is the included angle, we could say by the SAS congruency theorem that triangle SMR is congruent to triangle QMP. Nice. Finally, and most importantly, we have another proof. Now, this proof is a little bit hard to see. I apologize for that. So let's redraw this diagram down below. In the meantime, I'll talk to you about the problem. In this problem, we are making a canvas sign to hang up on the triangular portion of the barn wall shown here. We know, or we think I should say, that we can use two identical triangular sheets of canvas. We do know two things. We know that RP and QS are congruent. So if I take a look at this, and I label it Q, R, S, P, sorry, not congruent, they're perpendicular, my bad. RP and QS are perpendicular. So that's why I marked off this right angle here. We also know that PQ is congruent to PS. It says so right up here. And we need to somehow use side angle side to show that PQR, triangle PQR, is congruent to triangle PSR. In other words, the right-left triangle is congruent to the right. So when approaching a proof, we always want to write down our given. That's just a given. Wasn't actually that funny. RP is congruent to RS, or is perpendicular to RS. PQ is congruent to PS. And those are our givens. From here, what we want to do is we want to basically show a couple of things. We're really trying to show that these two triangles are the same. And again, there's a couple ways we can do that, the most convenient of which is going to be side, angle, side. So we know that a side is the same. We don't have any congruent angles marked. Let's think about that. What angle could be the same across both figures? While there are multiple different answers this could be, I think there's one that stands out above the rest. Let's take a look at this right angle here. We know that there's a right angle on the right-hand side, so don't we also know that there's a right angle on the left-hand side? In other words, don't we know that this is also a right angle? Well, yeah. We know that's going to be a right angle as well because these two are perpendicular. So it's going to make a bunch of right angles. We can say that angle QPR is a right angle. And it's because these two lines are perpendicular. So we can say by the definition of perpendicular lines. By the definition of perpendicular lines, these two are right angles. So now we know that these two angles must both be right. That means they're both congruent to each other. So angle QPR must be congruent to angle SPR. Why? It's because they're both right angles. And there's a theorem that we learned in Unit 2, the right angles congruence theorem, that says that all right angles are the same. Nice. Now all we need to show is essentially that the last side is congruent in both triangles. We need to show that this side here, PR, is congruent to this side here, PR. Wait, huh? Aren't those the same letters? In fact, they are. And we know that any time we have the same letters being used, we have a reflexive property being shown. We could say that by the reflexive property of congruence, that PR is congruent to itself. The only reason why I said PR and not RP is just because of the order in our answer here, but I wouldn't take points off if you said that PR is congruent to RP or something. Just keep that in mind. Last but most certainly not least, we know that a side, an angle, and a side on both of these triangles are congruent. So we can finish off by saying, by the side angle side congruency theorem, triangle PQR is congruent to triangle PSR. SAS congruence theorem. Very nicely done, y'all. That concludes our notes for 5.3. Have a fantastic rest of your day.